Okay, good morning. Let's continue on the triple integral. Finish that today. Okay. And hopefully we can get on a new topic. So far we have covered two different, evaluating the triple integrals using two different coordinate systems. Cartesian coordinate system and cylindrical coordinate system. So today let's look at the third one. Let's look at evaluate using spherical coordinates. So that's the third one. So let's take a look at what spherical coordinates is. In 3D space, if we have a point given, and you can certainly describe this point using Cartesian coordinates x, y, z, or you can use cylindrical coordinate using r, theta, z. So this time we'll use a set of three different variables. First, you can connect excuse me. You can connect this origin O, okay, with the point P, and we will denote the distance OP using variable rho. Okay, so that's the first variable actually. So basically it's the distance from point P to origin. And then use the angle between the vertical z-axis to OP and denote it as phi. So this is the vertical axis, so the phi angle is always starting from z-axis and then up to where the OP is. And then lastly, if you drop this point P into XYZ plane, and then if you connect this O with that point, there will be another angle from here to here. We call that theta. That's basically the polar coordinates or spherical or cylindrical coordinates theta. So your rho, phi, theta, so these three set of variables will uniquely describe the location of this point P. Okay. So you don't choose these three things arbitrarily. You choose the three variables so that it can uniquely describe the location of point P, just like x, y, z or r, theta, z. Okay, so as usual, when you have a coordinate system x, y, z, so this time we can have a spherical coordinate system. A spherical coordinate system can be set up like this. You draw a unit vector here. Let's call that E rho unit vector. So basically, this is the unit vector pointing in the rho direction. Right? This is like a reading directions, right, out of the origin. And then the next one is the unit vector in the phi axis direction. So this is angle, right? So phi axis is the rotation. If this is a z axis here, if this is an OP, then this is a phi angle here, right? So E phi is a unit vector basically perpendicular to that, and that's the direction of rotation for the phi angle. And lastly, you have the theta angle here, which is basically perpendicular to the theta there, and that can be this way here, so E theta. So now you have three unit vectors perpendicular to each other, so orthonormal to each other basically. So that's your spherical coordinates. And this is a spherical coordinate variable, rho, phi, theta. So what I would just want to emphasize is your phi angle here. Okay, This is from your z-axis to the OP vector or OP segment of lines. And the phi has a limit. Okay. Your minimum and maximum for the phi, okay, needs to be between 0 and the pi. So if this is the z-axis, okay, if this is OP, okay, your minimum phi angle, okay, 0 degree, basically when OP is aligned with the z-axis, or pi angle when it's at the bottom at here, okay. And I will see why we set a limit to the phi's range between 0 and pi, and we'll see why it's normal, why it couldn't be more than pi degrees. And rho at here, right? That's pretty simple. That's just the distance between O and the P. If you know your P is x, y, z, then your rho basically just x rho is essentially just x squared plus y squared plus z squared and then square root. Okay. So rho is naturally greater and equal to 0. And theta, as usual, it's the angle starting from x-axis and up to the projected line OP here. Okay. Theta, this is angle from x-axis to the projected vector OP, right, in xy plane. Okay, so these are the definitions of the 3 spherical coordinates. Okay. And next we'll look for the limits, and you basically need to be clear how phi or rho or theta are defined. As usual, let's look at the basically the connection. What's the connection between the spherical coordinate rho phi theta and the Cartesian coordinates x, y, z? Okay, so let's look at that. Geometrically, you can easily derive that. So what is x? So this is your x right here. Alright, so this is your x here, this part is y, and this part is a z. Rho x, y, z. Okay. Now, geometrically, we can easily derive for x, so this part at here, okay, this part. If I know the theta, if I know this portion at here, okay, then this is a theta. So x equal to basically the projected part, this part here. Let's call this as q here, right? So OQ times cosine theta. Right? I'll give you the x here. And then what is OQ then? The OQ is a projected segment of OP. And this is your phi at here. Okay, so phi here, phi here. So OQ basically equal to OP times sine phi, and then times cosine theta. And OP, the distance is rho, so it's a rho sine phi cosine theta. That's your x, right? So x equal to rho times sine phi times cosine theta. And similarly, you can get y equal to rho times sine phi and then times sine theta. So that's your y here. And finally, your z is rho times cosine phi, right? So rho times cosine phi give you the z component. So altogether, these three establish the connection between the Cartesian coordinates and the spherical coordinates. So this will be part of the formula. You don't have, I mean, you can remember this formula is fine, but if you can't, if you forgot, this is a way you can derive, okay, between x, y, z and rho phi theta. Okay. Alright, so let's take a look at a couple examples just to get used to the spherical coordinates here. Okay. So the reason we present a spherical coordinate is always basically you look at things from a different perspective. Okay, for the same thing, which is described, let's say for example, described in the Cartesian coordinates, then what does it look like to be described using spherical coordinates? So before we solve any triple integral question, so let's take a look at this first. Here is a sphere. Okay, so this is a sphere expressed in Cartesian coordinates. The sphere basically has a center at 0, 0, 1, and then its radius is 1. Right. So we can sketch this sphere. If this is 0, 0, 1, right, this is a point, and then the radius of the sphere is also 1. So basically, you can draw a sphere. Oh, that's not a good drawing. Centered around 0, 0, 1, basically. Okay, that's your sphere here. Okay. Let's say what would be the spherical, if I describe this one using Cartesian, it's like this, and if I describe this in spherical coordinates, then what would it look like? Okay. So all we need to do is we substitute x, y, z into this spherical x, y, z Cartesian equation in here, and then let's see what happens. Substitute x into here, substitute y here, substitute z over here. So we get rho times sine phi cosine theta square. So put a square in for each one of the term. Similarly for the y, so rho square sine phi square sine theta square. Put a z over there, rho cosine phi minus 1 square and equal to 1. So that's what happens after you directly substitute into the original xyz equation. Okay, so time to clean up things. Okay, always remember at this stage, the trigonometry, the simple trigonometry, the sine square plus cosine square equals to 1 can be used very neatly. For example, the first two terms, you got a common factor, rho square sine phi square. So take out the common factor, you're left with cosine theta square plus sine theta square. So the first two terms yields what? Right, rho square sine phi. Okay, and then this term, okay, rho cosine phi minus 1 to the power 2, okay, square. So let's expand it. Expand this term here. So expanding this term, so rho square cosine phi square minus 2 rho cosine phi plus 1 equal to 1. Okay. And then the first two terms, again, you have common factor rho square, rho square. So take out this common factor, you got left with the sine phi square plus cosine phi square, again is 1, so you're left with rho square. And here you got a 2 rho cosine phi, and this 1 and the 1 cancel each other, so, and that gives you this almost the final expression in here. So now you got another common factor rho and a rho at here, so take out the common factor, you got a rho minus 2 cosine phi equal to 0. And for this expression to be true, it's the solution either be rho equal to 0 or rho equal to cosine 2 cosine phi. And that's rho equal to 0 is not true, because if you look at this one here, it doesn't mean rho always equal to 0, right? If you pick a point anywhere on the surface of this spherical surface here, its rho is what? Its rho is from here to here. Okay? That's your rho. Apparently, it's not always 0, right? Except at this origin, it's 0 to 0. So your choice is rho equal to 2 cosine phi. Now, so basically, your original xyz equation, this one here, in a Cartesian coordinates, turn into rho equal to 2 cosine phi. And rho equal to 2, so basically, if I give you what is rho equal to 2 cosine phi, then in your mind, okay, it's actually a spherical, it's a sphere centered around 0, 0, 1. It's a little hard to imagine than this one here, right? It's definitely a little hard to imagine. Okay. However, you can do this. Remember, the equation basically describes this equation describes all of the coordinates, all of the points on the surface of the sphere. That's basically what this one does. Okay. So if I pick any point on the surface of the sphere, then that point should satisfy this equation. Similarly, if I pick a point on the surface sphere, that point should satisfy this guy here. Okay. So let's take a look at if I don't do this way here, if I just give you this sphere here, okay, let's use alternative way to derive this one. I'll pick a point on the surface sphere, okay, and I know from here to here that's your rho here, right? And also I also know that from the z-axis to this line, what's the symbol representing here? From the z-axis to here, which is what? From z-axis up to here. What's this angle? Phi. Good. So this is your phi here, right? Okay. So without doing anything, you labeled basically according to your spherical coordinates. Okay. And then I will use a property associated with the spherical surface. So when you have a point on the sphere, and what you can always do is, let's just suppose I pick the point just happen to be on this circle here, okay? On this circle. You can always construct from this point up to here, you can always construct a triangle like this. Okay? Yeah. Or let me maybe draw it just slightly differently. So let's say if I pick a point somewhere here, okay, somewhere here, then you can always basically create another circle passing through that point. That makes sense? Right. So basically, anywhere, any point you picked on the spherical surface, you can always create another great circle passing through that point. Okay. It's like a slice of the orange. And then for this point P, you can create essentially a triangle by always connecting the top vertex with that point and using that diameter, right, basically as another edge of the triangle, and this OP as another edge. And one of the property is this triangle is always what? A right triangle. Okay. So essentially, when you have a circle, pick any point right on the circle, and you got a right triangle here. Is that good? Yeah. So now, if I have this right triangle here, as I did, I know this is a rho at here, and this angle is phi at here, right? And from O to the top vertex, and from the bottom here to the top vertex, what's the distance from here to here? 2, right? That's the spherical surface, and this is a sphere here with a radius of 1, so the diameter basically is 2. So basically what I get here is, here's a 2, here's a rho, and here's a phi. Make sense? Yeah. And this is the general point we have picked on the surface of the sphere, right? Yeah. So then what's the connection between this rho and phi here by looking at this right triangle, which is what? Cosine phi equal to rho over 2, right? Rho over 2. Yeah. So rho over 2, then you get rho equal to 2 times cosine phi. That's exactly the results we have derived here. Okay? Yeah. As a matter of fact, next you'll see when we have a spherical surface like this, and you're going to probably look for the limits for the rho, and that's how we can find the limits of the rho. Okay? Yeah. Okay. Very similarly, you can apply similar approach to the other type of surface. So for example, if I have a cone z equal to x squared plus y squared. So we did this cone last time using cylindrical coordinates. When you have a cone like this, if you describe this using cylindrical, okay, if you recall that, what do we do with cylindrical? In cylindrical coordinates, you replace the x and y with r times cosine theta and r times sine theta, right? And you basically get z equal to r. Okay, so for this cylindrical surface, you get z equal to r in cylindrical coordinates. So how about in spherical coordinates for the same cone right here? So we can do the same approach as what we did for the sphere. We substitute x, y, z with the three expressions at here. So basically here we can substitute z with rho times cosine phi, and then substitute the x, y with rho times sine phi cosine theta square plus rho times sine phi sine theta square. Yeah. Okay, so substitute your x, y using the expression, okay, between x Cartesian and spherical. Substitute and then simplify. Now this time you'll end up with a very simple solution. Just say phi equal to pi over 4. Okay. As a matter of fact, if you remember, right, this cone basically has an edge with 45 degrees between the edge and the z-axis. Right. Every edge has this angle. Okay. So in spherical coordinates, it's even simpler. Just phi equal to pi over 4, okay, for the same cone. You can see, so basically the three expressions express the same thing. Good? Yeah. Okay, so let's focus on how do we evaluate the triple integral using spherical coordinates here. Okay. Yeah. Here is the triple integral. Okay. This is an expression we typically use for Cartesian coordinates, but if we wanted to evaluate the same thing using spherical coordinates, so basically we're going to get rid of x, y, z and replace everything with rho phi theta. Okay. So how do we do that? The easiest part is the function f. We can replace the x with rho times sine phi cosine theta. Replace the y with rho times sine phi sine theta. The z with rho cosine phi. Okay. So that expression, whatever that expression is, you can replace the x, y, z with the three expressions that are here. And then the dv, okay, used to be dx, dy, dz, or whatever order that you choose. Okay, that's in Cartesian. But this time we're going to replace the dv, right, using our d rho, d phi, and d theta. So that's our three integration variable now, right? You know, in spherical coordinates. However, as we learned, it's not going to be just simply replacement. There's going to be some kind of a scaling factor at here. And how do we find the scaling factor? Jacobian, right? Exactly. Okay, excellent. So again, Jacobian basically is the J equal to the determinant of the 3 by 3. Well, here basically is the determinant of the Jacobian, absolute value of the determinant Jacobian, right? Yeah. And first you create the Jacobian matrix. Partial x over partial rho, partial x, partial phi, partial x, partial theta. Okay, so similarly for the other two rows here. I'll leave this as an exercise for you to practice. Okay, so your xyz expression is already given, which is this one, right? Where is it? Where is my xyz? Here. Your xyz expression is given here. All you need to do is calculate the 6 partial derivatives and then put it over into this 3 by 3 matrix. Okay. Then you can calculate the determinant of this Jacobian matrix set here, and it turn out to be rho square sine phi. Okay, rho square sine phi. And rho square sine phi, then you replace that over here, get the determinant of it, get the absolute value of this, and then replace it with this term here. So rho square sine phi, right? How do I, what about the absolute value of this? Rho square is naturally a value greater than 0. Sine phi, what's the range of phi? 0 to pi. So when phi is between 0 to pi, the sine angle is guaranteed to be positive, right? So you don't have to do anything, just basically replace that over here. Okay. Then your evaluation, right, of this triple integral basically will become all in terms of this rho phi theta now. Is that clear? Okay. And the next step, of course, how do I find these integral limits basically? Okay, that's your next step. Okay, so let's find the integral limits using an example here. Okay, I'll show you through an example. How do we find the integral limits for rho phi theta? So here we're given a real ice cream cone here. So here what happens is you have two surfaces. Okay. The bottom surface is z equal to x squared plus y squared. Okay. That's basically the cone that we have been talking about. Actually, sorry, this is 1 over root 3. And then root x squared plus y squared. So a little bit in there, a wider cone right here. Okay. So the previous cone we have talked about, there's no 1 over root 3 right here. So I put a 1 over root 3. Okay. And then on the top of the cone here, you have a surface. Basically, that's the top of the ice cream here. So that's x squared plus x squared. Yeah. X squared plus y squared plus z squared equal to 1. So this surface, okay, or this object has two surfaces. On the top of the surface, it's this, and the side surface is this. Okay, yeah. So two surfaces. So let's look at what is the volume. Okay, what is the volume of of this ice cream. Volume. To calculate the volume, basically, if you look at the triple integral, essentially this function here, if this is equal to 1, then you get the volume of this region D. Okay, so let's look at the volume of this guy here. Basically, now we're calculating this guy. So the typical steps. First step, sketch the region D, okay, which we have just sketched at here. And the question maybe just give you a simple language description. You have, let's say, for example, say region D is bounded by a sphere x squared plus y squared plus z squared equal to 1 and a cone of this. Right? That would be the description. And then you can sketch that using this description. And second step is we still need to draw the shadow, because we need this shadow for the theta. Yeah, we draw the shadow of region D in xy plane. And step number 3 is well, actually, I should have mentioned this. There should be a selection order for integration as always, right? Selection order of the integrals here, very much like the cylindrical, or a size or a Cartesian. You basically can have 6 different combinations. Okay, but for spherical coordinates, most of the time is d rho, d phi, and d theta. Okay, so that should be suffice to do the calculation. You can certainly choose a different order for sure. You can basically, right? But the d rho, d phi, d theta, okay, for most of the time for our cases will be enough. So we're gonna go with d rho, d phi, d theta. Just like cylindrical, remember I demonstrated dz, dr, d theta, right? As a typical order we use for cylindrical. But if you choose a different one like dr, dz, d theta, or dr, d theta, dz, and I showed you how you can find the limits too. Okay? It's a little unconventional. Okay, so step number 3 is finding limits. Finding limits, always remember, okay, it's about scanning through this region D. And it doesn't matter which coordinate system you have chosen, scanning through the region D basically means you have to scan according to the order, and then you always basically go steps. First step is rho, then you scan in the rho axis direction. Second step is phi, then you scan in the phi axis direction. Last step is theta, then you go scan in the theta axis direction. Very much like XYZ, right? Scan through the XYZ axis direction. Okay. So let's find the rho limits. Find the rho limits. Finding rho limits is about scanning in the rho axis direction. What is rho axis direction? Remember this x, the coordinates since I draw it in here. Rho axis direction basically it's this direction, right? So you gotta go basically scan in this direction first. So let's come back here. So what we do is we draw a reading line from origin through the region D. Through the region D. So that's the scanning direction here, right? So starting from origin at here, and you draw a reading line, okay, out of this region D at here. So let's scan in that direction, see how much we can create this surface. So when you go from here along that direction, so basically you have a first contact over here, then you have a second contact, okay, somewhere on the top of the surface here. So the first scanning give you a first contact, which rho mean apparently is 0, and the second contact is the rho max. So rho max in this case falls onto the top surface, which is this spherical surface here, and this is a sphere centered around the origin. So what do you think the rho max is? 1, right? It's always radius 1 because it falls right on the surface of the sphere, which is centered around the origin. This is a difference with the other sphere centered around the 0, 0, 1, right? The one that I showed you. Okay, so when you have a sphere centered around the origin, your rho is always equal to 1. So your rho max is equal to 1 here. Okay. So that's the first scan. So basically the first scan, if you think about it, what you have just created, it's like you created a small segment of a line like this here. Okay? Yeah. So you create it from here to here, you create a line here. The second scan, we're gonna rotate this reading line, okay, in the direction of the phi axis, because that was second order here. So phi limits, rotate the reading line starting from your z-axis here, because your z-axis is the starting point at the phi angle, always the phi angle here. So you rotate it from z-axis all the way across this region D. And find where the starting, where is the where the edge is, you know, as a boundary of this region D at here. And apparently, if you do the scanning, it's the starting point is here, and then when you scan through, okay, the end point is always what? Right on the edge of this cone right here. Okay, so starting from here and end on the edge of the cone right here. That make sense? Yeah. So from here to here. Okay. So your phi will have a phi mean as a first contact, and then second contact according to the two edges. Okay, to the edges here. Your phi basically find the two edges. The two edges give phi mean and phi max. Phi mean and phi max. Phi mean is pretty easy, and that's 0 degree because that's starting from z-axis. Phi max, as we draw here, phi max falls as basically the angle from the z-axis to any edges, right? To any edges on the cone surface. Okay. Hey, and here's the cone here, right? Here's the cone. Okay. So how do I find the phi angle then? So what will be the phi here? We actually did that in the previous lecture. If we just have the cone, if I just draw the cone here, okay. If I just draw the cone, you have a couple of options you can try to find this phi angle at here. Okay, find the phi angle. Now one option is actually a little more straightforward one, but it requires a little careful calculation. Just like what we did in this example. You substitute x, y, z with the expression for the spherical coordinates. X is this, y is this, and z is this. Substitute everything, right? And simplify. Find a solution. Like this, you get a phi equal to pi over 4. It's okay, right? And similarly, you can do this for this. You'll get a phi equal to pi over 3, so 60 degrees for this cone here. Okay, that's one approach. And the other approach, I think, I don't know if you remember, basically, you could, what you could do is, you could use like the idea of the cylindrical coordinates. When you substitute x, y with r cosine, r sine into here, you'll get a z equal to 1 over root 3 times r. Okay, 1 over root 3 times r. Basically, what that means is, okay, you can create, if you pick any point, okay, on the cone surface at here, and you can always create a right triangle at here. Okay, if you pick any point, you can always create a right triangle. For this right triangle, so what you see here is, if I bring out the right triangle, here's your z, here's the r. Okay, so this is z, this is r at here, and here is the phi angle. Okay, so this is your phi angle here, z and r. Okay. So if I look at this right triangle here, and look at the geometry, so tangential phi equal to r over z. So that's a general relationship between the r and the z here. And then you have z equal to 1 over root 3 times r. So replace the z over here, and then the whole thing equal to root 3. Okay, root 3 here. So tangential phi equal to root 3, your phi angle is 60 degrees, pi over 6. Pi over 3. Okay. So that's another approach to get this phi angle at here. Okay? Yeah. Then often in time, you probably want, I don't give you very sophisticated cones if there's a question. Okay. There may be two cones you can remember. One cone is this guy, basically phi equal to pi over 4, right? Another cone maybe is this one, 1 over root 3, then you get basically phi equal to pi over 3. Okay. So that's how you can find the phi limits. So finally, it's the theta limits. Okay. Theta limits are based on the shadow at here. So here is the cone, and here's ice cream cone here. So what's the shadow? I think I said the second step, draw the shadow. I didn't draw the shadow at here. So if I draw the shadow, project everything onto the xy plane. So the shadow essentially is going to be a circle. Yes? Yeah.
So I will find I already start from 0 to 60. How about do we consider the other side, like negative? Do we have like negative?
No, you don't have. Remember the limits for the phi is between what? 0 and pi. We have limited the phi angle to be between 0 and pi here. So you cannot have a negative angle, basically. Yeah.
So phi equals to 0 is z-axis.
Yeah, phi 0 basically when align with the z-axis, that's phi equal. Counterclockwise. It's always counterclockwise. Yes. Yeah. When you count angles, right, it's always counterclockwise with respect to the reference axis. Yeah. Is that good? Yeah. So, coming back to this, what does the second step do, right? Second step, when you rotate basically the reading line from 0 to pi over 3. So the second step, basically, this line here, you created what? You created this half of this, not a circle, but from here to here, right? This kind of small segment of the shaded area. Okay, that's your second scan. Okay. And last step, which is the theta angle. The theta angle is based on the shadow here. So here's a shadow, and this is the projected vector of this reading line here, and you rotate that projected vector across the shadow, right? And see the edges, okay, covering this shadow. In this case here, apparently it's 360 degrees, starting from 0 and then 2 pi, right, covering the whole shadow here. So your theta here is to sweep through the shadow, okay, through the shadow, and find theta mean and max, and find theta mean and theta max. So in our case, theta mean is 0 and theta max is 2 pi. So now you have all the limits, and put down all the limits set here. Okay, we're talking about just the volume. So you have a rho square sine phi. Remember, this is the determinant of the Jacobian. And then d rho d phi d theta. Rho goes from 0 to 1. Phi go from 0 to pi over 3. Theta go from 0 to 2 pi. Okay. So that's all the limits and all of the expressions. Okay. This should be a very simple integral set here, even though there are 3 integrals, but there's very straightforward. The first integral is about the rho, right? So 1/3 rho cubed, and substitute limits. Second step about the phi. So basically about the integral sine phi. Yes. Theta limits or phi limits? Theta? Then whatever the actual theta limits is, right? So your theta still starts from, your theta still should start from this x-axis. So basically, oh, you're talking about phi limits. Yeah. So your phi doesn't matter. So always start from z-axis, right? See if you have an intersection between this line and the region D. If there is, then your theta mean is 0. Okay? And then always go counterclockwise until you hit the edge of the region D. Then the phi max is from the z-axis counterclockwise to wherever the edge is. So it doesn't matter whether you have a symmetric region D or not, right? So the phi limit is always from, if you have an intersection from here, then it's 0, right? And wherever the edge is for the region D, it's there to the edge. Yeah. What do you mean one side is 60? Irregular cone. How irregular? On the left side? You mean this side here? Oh. I see what you're saying. So you're talking about like that. This is like 80. and this is like 60 here. Is that right? Yeah. Well, then your cone equation is not this equation anymore, right? Does that make sense? Yeah. But your rho probably also going to be different. But you can still follow this scanning rho phi theta. See if you can still create this cone at here. Does it make sense? See, you can still follow the process because I can still create in the rho direction, right? I can still create the phi at here. Okay? So basically, you still need to follow this rho phi theta scanning at here, and the phi needs to be consistent. Consistent basically means the phi angle has to be always between the z-axis and whatever the edge is. And then last step is still this rotation, the scanning rotation there. Okay, because it's just the expression is different now, right? The expression, yeah. It's like a 3D printing essentially. Okay. Good thinking, yeah. I hope I can come up with the actual examples there. I can think of an example, maybe half of this cone and half the other cone, right? Yeah. Okay. So let me think about the example and maybe we can try it later. Is that clear? Okay. So for this one, so let's come back to maybe another question here. Come back to why the phi has to be between 0 and pi as this policy, right? As a constraint here, basically. Why does it have to be theta? Why not 0 to 2 pi? Can we do phi, let's say 0 to 2 pi? Let's use a sphere to illustrate the idea here. If I have a sphere, yeah, here's a spherical surface. So this time I'm gonna do rho first. So that give me first scan, give me what? From here to here, give me one small green segment. That's your first scan, right? Second scan, if I do phi 0 to 2 pi, it basically creates from here to here. But this time, if I do phi from 0 to 2 pi, what do I create? From here and then all the way up to here, right? So basically the second step, if I do scanning 0 to 2 pi for the phi angle, so starting from here, then you create all the way back, that's 360 degree, and you create a circle, right? And last step, according to our it's a theta scanning. The theta scanning is what? Again, it's a shadow 0 to 2 pi. Now, can you see the problem now? So when you have a big circle at here, and then you sweep the big circle 660 degrees, rotate about z-axis, what do you create? Huh? You have a, think about using SolidWorks. When you have a circle, you wanted to sweep that circle 360 degrees. What did you create? If it's a half circle, and if I rotate the half circle 360 degrees, what do I create? A sphere, right? But if it's a full circle, and then you rotate 360 degrees, now what do we create? Torrent?
Yeah, donut.
Well, no. I don't think you can create a donut. You create the sphere twice, basically, right? So that's the redundancy we're talking about. You're trying to scan through this without redundancy. If I only have half of this and then rotate 0 to 2 pi, 360 degrees, I scanning through this region uniquely without any redundancy. But if I have another half edit here and do the same 360-degree rotation, then we're basically creating the same region twice. Okay. As a matter of fact, you can try it. If you're using any CAD software, it won't let you to create. When you punch in 360 degree and they give you an error message, it says there's some sort of a redundancy or whatever, right? Exactly what I just said. So alternatively, if you have a full circle and you want to create a sphere, how can you rotate? Instead of 360, you can rotate what? 180. Okay. Now back to the triple integral. So you might argue, can we let phi define this as the constraint, and then theta let it go theta instead of 0 to 2 pi and go 0 to pi? Yes, you can. But however, the convention for the spherical coordinates has been set, which is the phi, not this, but this. That's the convention. Okay? Convention means we have to follow. And when you become famous enough, then you create your own convention, then we follow you, right? But for now, we follow this one here. Is that okay? Yeah. So that's the idea of why phi has to be 0 to 2 pi. Never create a phi limits beyond 0 or beyond pi. Okay. So finally, I don't need to go through too many examples, but just bear in mind of the idea of the 3 steps of scanning in the direction of rho, phi, and theta to go through, to sweep through the whole region D without any redundancy. Okay? Yeah. So the final topic for triple integral is applications of a triple integral. And I will go through very quickly because we spend a lot of time talking about applications of double integrals. Okay. Many of these applications here essentially just adding one integral signs compared to the double integral application. For example, we can calculate mass. When we calculate mass, we need a density function. We call that delta. So the density will basically calculate the mass. If you think about the double integral, all we need is just add one single integral sign, become a triple, and then you have your density function delta times the dV here. So that gives you the mass of this solid region D. Very easily you can think about it basically when you have a density times dV, this is like their small mass dm and here, right? And then we integrate or adding or summing all of the small masses together, you get a total mass of this region D. So that's your mass. There's another concept called the average value of this function f of xy in region D. Just like the average value of f of xy in the region R, right, for double integral. So if you recall that when you have a double integral region R, then there's a function f of xy. We illustrated the f of xy as a height, right? So there's a function on top of the region R. So then what's the average height, okay, over this region R? But unfortunately, when we see the function f of xy, okay, with respect to region D, so 3D limits us from any further imagination, so we cannot just say this is height or this is anything else, right? So we can just say this is average value of this function in the region D. So f bar is the average value, and that's 1 over the volume of this D, and then triple integral this function f x y z dv. So that'll give you the average value of this f over the region, over the volume, the region D. Maybe this is temperature, right? Maybe this f represents the temperature for every point inside the region D. Then what's the average temperature within this region D? So this is average, and then we have the weighted average. So the weighted average f right here. The weighted average, we use a density function like the double integral as the weighting factor or the weighting function. So we can use a similar one here. So f bar equal to 1 over this mass of the region D. Okay. So if you have a solid represented by the region D, this is basically what it means. Mass of the object. Triple integral function f. This is the weighted average function f, weighted by the density function dv. So basically, this portion here is the weight. So if you compare your notes with the double integral, the difference is here's a triple, and the difference that here is the mass of the d instead of the mass of the small plate r. Okay, so that's your third application, and then we have this center of mass. Now this time it's much more actually general because we're talking about 3D objects now instead of just a thin plate. So this center mass is more, the formula here is more general, more useful. We have x bar. Basically, when you're talking about the center mass, it's this weighted average function f. You replace this f with x, you get x bar. Replace the f with y, you get a y bar. Replace the f with z, and you get a z bar. So x bar equal to 1 over this mass, and x over here times the density function dv. And similarly, you can write down y bar and z bar. Okay, so try yourself. So all you need is just replace the f with y and z. So this way you get the center of mass. So this is a very useful formula. All good? Yeah. In terms of evaluation, no difference with from any other triple integral evaluation. If you have this is typically will be given density function, and d will also be given. So place everything. And the next step, when you calculate x bar, y bar, z bar, is you consider, so what coordinate system should I choose? Should I choose Cartesian, cylindrical, or spherical? Okay. So there are only 3 choices. And when you choose the coordinate system, sometimes there's some general guidelines you can follow. If you're dealing with, for example, a cylinder, so typically you'll choose cylindrical coordinates, right? If you're dealing with an object consisting of a spherical surface, then you probably would choose spherical coordinates. And then moment inertia. Okay, so moment inertia. Moment inertia again is always about certain axis. So this is a very general moment inertia now because we're talking about 3D object. So if I have a 3D object at here, okay, enclosed by the region D, enclosed by the region D. So now you think about this object. Then what is the moment inertia of this object about a certain axis? So for example, maybe about the z-axis, maybe about the y-axis, or maybe about this x-axis. And moment inertia is about how hard is it to impart a rotational motion about that axis. Okay? But typically, the formula is, okay, if this is a region D representing that 3D object, the formula is always basically the distance to the rotational axis squared. Okay. So here's the distance to the rotational axis. For example, I'm going to pick a very small mass over here. Here is a small mass dv. What is the moment inertia of that small mass with respect to certain axis? So what do? You need to calculate the distance from the small mass to that axis, and then square it, and then times this dm at here. So dm times the distance square give you the moment inertia of the point mass. Then you add all them up, you get the total moment inertia essentially of the whole object with respect to the axis. And dm equal to the density function times dv at that location. So if you have a small cubit here representing volume, then dm equal to the density times the dv. So I can replace the dm with the delta function times dv. That's the general formula for moment inertia with respect to certain axis. So now we can think about the special moment inertia. What would be the moment inertia about the z-axis? And we will use Iz, okay, to represent the moment inertia about the z-axis. Follow the formula here. About the z-axis, basically, if I pick this point at here, pick this point, then what would be the distance from that point to the z-axis? If this point I picked is x, y, z, okay, with the coordinates x, y, z, then from here to the z-axis, the distance is what? This distance. X squared plus y squared square roots. Okay, that's a distance. Okay, and you can maybe I'll demonstrate a little bit more here. So if I pick a point at here, and I can always create, this is your y, this is your x, this is your z here, right? The coordinates. So the distance from that point to the z-axis is this portion at here, which is this portion. Okay. So the portion at the bottom here, you can literally see it's square roots x squared plus y squared. Right? Okay. So then your Iz equal to triple integral. Replace the distance with x squared plus y squared, and then squared, and times the density function dv. And this square here, you can get rid of the square root, and that basically gives you just x squared plus y squared. So this is your moment inertia about the z-axis. Okay. Similarly, you can get what will be the moment inertia about x-axis. Use the same approach, finding distance from a certain point to the x-axis, which is the square root y squared plus z squared, and then put it into the formula, you get this. Okay. So try Iy. So what would be the y moment inertia about the y-axis? So all of the applications, as you can see, are pretty much just one-step expansion from the double integral, right? The idea is exactly the same thing. Okay? Idea is exactly the same. So I'll show you one example, then we can basically just wrap up here. Okay? So let's take a look application example here. I'll take my favorite cone, and here we have a cone z equal to a times square root x squared plus y squared. Okay, so this time is a general coefficient a over here, and the top of the cone is cut by a plane z equal to b. So basically, you have a plane on top, okay, and then cut it at z equal to b. So you got your region D is between z equal to b and z equal to x squared plus y squared square root times a. So here's region D, and I want to, and then also we're going to assume my density for the region D is 1. So let's make it a little simpler. And I want to calculate what is the moment inertia of this object with respect to the z-axis. So sometimes a lot of time when you have an engineering handbook, if you open the engineering, you try to find a regular ship. It may have a table actually to give you all the moment inertia for these things here. Okay, but let's calculate this moment inertia. Okay, using our formula, we have our formula Iz already written down. So x squared y squared times delta and dV, and density in this case is 1, so that makes our life a little easier. Okay, so that's the formula for the moment inertia about the z-axis now. Next step is exactly what I mentioned. What coordinate system shall we use to evaluate this triple integral? What do you think? Which one would you pick? Cylindrical. Okay, good. I would pick a cylindrical. Spherical would also work actually, so you can try, right? So let's use cylindrical. Using cylindrical means a couple of things that you have to do before you start, putting everything together. First thing you need to do is this dV will be, instead of dx, dy, dz, will become r, dr, d theta, dz, right? So that becomes this. So there's always order. What do I have? R squared? No. R squared, just R here, right? Yeah. Huh? Yeah, dV is r, dr, d theta, dz, right? Yeah. So this your dV, you need to change that, and x squared plus y squared, you also need to change to the cylindrical coordinates. So your x is r cosine theta, y is r sine theta. So those things, just some of the prep work, then the x squared plus y squared becomes r squared. Finally, okay, putting things together is then we try to find the limits now. Okay, yeah. So Iz equal to 1, 2, 3 r squared times r. Okay. Now dr, d theta, dz for cylindrical, remember the order, we typically follow dz, dr, d theta. Okay. Not that you can use the other order, but typically dr, dz, dr, d theta should be enough, okay, for most of the cases. So now let's find the limits for z, r, theta. So let's find the limits. Here is how we found the limits. If you recall how we found the limits for the cylindrical, right? First step, draw the shadow of this region D, okay, in the XY plane. And label the shadow, okay, because you need a shadow to find R in theta. So what's the shadow? The shadow basically is the projection of the top surface into the XY plane. And top surface is the intersection between the plane z equal to B and this cone at here. So guess then what's the top surface? The top surface, substitute B over here to the Z, so you get B equal to A times x squared plus y squared. Right? That's the intersection between the plane and the cone. And then simplification give you x squared plus y squared equal to B over A squared. So basically the shadow is a circle with a radius of B over A. Okay. Once you get this done, follow the procedures finding limits. Pick a point inside the shadow, then draw an arrow line in the positive z-axis direction. First contact give you z mean, second contact give you the z max. Z max, pretty simple, that's the top surface, so it's always B, right? So always B here. So Z max is always B. Z mean, which falls onto the cone surface. Here's a cone in here. So we change this cone into what? A times, if you recall that. Replace xy with r cosine r sine, so the cone becomes a z equal to a times r. Okay. So everything is in cylindrical. So your z mean in this case is this cone expression. So that's AR. Okay. So that's your z mean, AR. R limits are based on the shadow. So you draw a reading line out of this shadow here. First second contact give you R mean R max, and that's basically the circle right here. So 0 to B over A. Finally sweep the reading line 360 degree across the shadow, and that's 0 to 2 pi. So here is all the limits, right? And this is your rest of the integration terms. It's a very straightforward integration, and you should get pi b to the power 5 10 times a to the power 4. Maybe 3 or 4 years ago, this is one of the final exam simple question about 10 points. Okay. Yeah. Most people get it. A lot of people are making mistake in terms of the integral limits. But the danger is, you make one mistake in the limits, the rest of the calculations are all wrong, right? Yeah. So this is why at this stage, practice, getting more experience with finding the limits at here. Okay, so that's basically all about triple integral. Okay, and kind of running time. From next lecture, we're going to go back to the vector field, and we'll start to do integration within vector fields again. Any questions? Okay. Good. Thank you.